The universe's endless dance. What it really means to expand into nothing. Right now, as you read these words, the universe is bracing outward so fast that the space between distant galaxies is stretching by thousands of kilometers every single second. But here's what really messes with your mind. It's not expanding into anything. There's no cosmic warehouse waiting outside, no boundary line, no bigger container for it to fill up. If you enjoy these kinds of quiet, profound journeys that shift how you see the universe and reality itself, you might consider subscribing and liking this episode before we dive into existence's deepest mystery. Your support helps these explorations reach more curious minds. Now, prepare your mind for this big question. Our journey begins. The balloon that breaks our brain. Picture a balloon inflating in the room where you're sitting. As you blow air into it, the rubber surface stretches outward, pushing against the surrounding air to make room for itself. The balloon grows because there's space for it to grow into. Your room provides that space. This makes perfect sense to us. In our everyday experience, expansion works exactly like this. But the universe gently smiles at our logic. When cosmologists tell you the universe is expanding, your mind instantly imagines that balloon. You think of space stretching outward into some vast emptiness, waiting like a cosmic room to be filled. You assume there must be a boundary where our universe ends and something else begins. This way of thinking feels natural, even obvious. This is where physics shatters our comfortable assumptions. The universe isn't like that balloon. When space expands, it's not pushing against anything. There's no cosmic living room, no container, no outside. As the universe grows, it creates the very concept of space itself. Think of it this way. Imagine trying to draw a circle on a piece of paper that's bigger than the paper itself. Impossible, right? But instead of getting a bigger piece of paper, the paper itself magically grows to make room for your circle. This idea sounds impossible because in our world, everything expands into something else. Plants grow into air, cities sprawl into countryside, ice spreads across water's surface. There's always somewhere for the expanding thing to go. There's always a boundary between the thing expanding and the thing it's expanding into. But what if you're both the picture being drawn and the paper it's drawn on? How we discovered this mind-bending truth. Scientists discovered this brain-twisting reality by watching distant galaxies. Edwin Hubble noticed that galaxies farther from us were moving away faster than nearby ones. At first glance, this creates the impression that we're at the center of some cosmic explosion, like we're standing still while everything else flies outward into empty space. But reality is far stranger and far more elegant than that. It's not the galaxies themselves that are expanding, it's space itself. Galaxies aren't moving through space, the space between them is continuously growing. Imagine dots on the surface of a balloon, but run the process in reverse. As the balloon inflates, the dots move apart without ever moving across the surface. The surface itself expands. Every single dot sees all other dots moving away from it. No dot is special. No dot is at the center. Now, replace that balloon's two-dimensional surface with the three-dimensional space you live in. The universe isn't expanding into anything because there is no anything for it to expand into. It's recreating the stage itself, the very arena where expansion happens at every moment. This breaks our intuition so deeply that even the brightest scientists struggled with this idea for decades. Einstein himself initially rejected it. Yet this seemingly impossible expansion is happening right now, faster than you can even imagine. The light that proves everything. The foundation of this mind-bending idea, that the universe isn't expanding in a container, but that space itself is stretching, rests on solid evidence. Scientists didn't reach this conclusion through philosophical speculation alone. They carefully read messages from the universe itself. That message was light that had been traveling through space for billions of years, and the secret it carried revealed the nature of expansion beyond any doubt. It all started in the early 20th century with Edwin Hubble's revolutionary observations using what was then the world's largest telescope. Hubble proved that the fuzzy objects known as spiral nebulae were actually their own galaxies, millions of light-years beyond the Milky Way. But his truly shocking discovery came when he examined these galaxies' movements. Almost without exception, every galaxy he observed was moving away from us. Even stranger, the farther away a galaxy was, the faster it seemed to be receding from us. This was the perfect proportionality between distance and recession speed, known as Hubble's law. At first glance, this might create the illusion that we're at the center of an explosion, with everything flying away from us. But there was a deeper, more elegant explanation. The same view would be seen from any point in the universe. Galaxies weren't flying away from us through empty space. They were being carried along by space expansion itself, like raisins in rising cake batter. Wherever you are in the batter, all other raisins appear to be moving away from you, and the farther raisins recede faster because there's more batter between you expanding. While this analogy helps us understand intuitively, it doesn't prove space itself is expanding. The real proof emerges when we understand how light itself is affected by this expansion. When a distant galaxy sends a beam of light toward us, that light begins its journey with a specific wavelength: blue light, red light, ultraviolet light. Each has its own signature. But as this light travels through expanding space for billions of years, something extraordinary happens. As the fabric of space beneath it stretches, the wavelength of light stretches along with it. Think of it like walking on a rubber band while someone else slowly stretches it. Even though your step size doesn't change, the ground you're covering is lengthening beneath you, so your journey takes longer than expected. Light experiences something similar. But since its speed doesn't change, this stretching manifests as an increase in wavelength. A photon that set out billions of years ago as bright blue light arrives to us having transformed into tired, lower-energy red light. This phenomenon is called cosmological redshift, and it's fundamentally different from an ambulance siren becoming lower-pitched as it drives away. Light redshifts not because the galaxy is moving through space, but because space itself expanded during the light's journey. Every single wave of light is forced to stretch as the cosmic fabric beneath it grows. This is the most direct evidence that space behaves as an entity in its own right, independent of the objects within it, with its own dynamics. The scale of this effect is dizzying. Light from the most distant galaxies we can observe has been stretched to nearly 40 times its original wavelength. This means the scale of the universe grew 40-fold during that light's journey. What began as dense ultraviolet radiation now reaches us as faint infrared heat. This shows us not only that expansion is real, but also how colossal and relentless a force it's been throughout the universe's history. Expansion is woven into the fabric of the universe. It's one of its most fundamental features. Why your room isn't getting bigger. Cosmological redshift shows us beyond doubt that space is expanding at massive scales across billions of light-years. But this immediately raises another question in our minds. If space is expanding everywhere, why don't we feel this expansion around us? Why aren't the walls of this room moving apart? Why isn't the distance between your eyes and the screen you're reading constantly increasing? The answer lies in the balance of scale and strength among the forces governing the universe. While space expansion is a tremendous force on cosmic scales, it's extremely weak and delicate on local scales. Right now, the space in this room really is trying to expand. The emptiness between the atoms holding you together wants to grow larger. But there are other forces opposing this expansion tendency, forces trillions upon trillions of times stronger. The electromagnetic force holding atoms together easily overpowers space's expansion. The molecules in your body stay together thanks to this force. Similarly, Earth's gravity keeps you and everything around you bound to the planet. The Sun's gravity holds the solar system together. The Milky Way's collective gravity unites hundreds of billions of stars in a single galactic structure. Within their domains of influence, these forces completely neutralize the gentle pushing created by space expansion. Expansion is like a mild current on a river's surface. A strong swimmer, gravity or electromagnetism, can easily swim against this current. But in the vast voids between galaxies, things are different. In these immense darknesses stretching across millions of light years, there's no meaningful gravity or atomic force to hold space together. In these voids, nothing resists the expansion current. That's why space expands freely in these regions, carrying galaxies apart like raisins in rising cake batter. The raisins themselves, the galaxies, don't expand because their internal bonds are stronger than the batter's rising. But as the batter between them expands, they inevitably move apart. The question that collapses. This brings us back to that fundamental question from the start of our journey. If expansion is space's own intrinsic property, showing itself only where forces are weak, then why does the question, what is the universe expanding into, logically collapse? Because this question ignores the fact that you're part of that cake batter yourself. You're asking what the batter is rising within, but the questioner is also made of batter. Concepts like outside or into require an observer standing outside the system being observed. You can observe a balloon's expansion because you're outside the balloon. Your room provides an outside for the balloon. But when it comes to the universe, by definition, there is no outside. If there were, it would also be part of the universe. The universe is the sum of everything that exists. Therefore, the universe's expansion isn't the movement of one thing toward another thing. It's the system itself changing scale through its own internal dynamics. This isn't just wordplay or philosophical dodging. It's one of the deepest conclusions of Einstein's general relativity theory. The theory describes space and time not as separate things, but as a dynamic whole called space-time that forms the universe's fabric. This fabric can be bent, curved, and yes, expanded by the matter and energy within it. Expansion is something this fabric does to itself. It doesn't need an external arena. It's constantly recreating the stage where expansion can happen. So the question, what is the universe expanding into, isn't an unanswerable question, it's a wrongly asked question, like asking what's north of the North Pole, or what does the color blue sound like? These questions become meaningless because they try to go beyond the boundaries of the concepts they use. Understanding the universe's expansion requires setting aside our intuitions and accepting that reality can be far stranger and far more fascinating than our everyday experiences. The cosmic prison we can never escape. Every night when we step outside and look up at the star-filled sky, we feel like we're seeing the universe, everything that exists. That dark sky seems like an infinite canvas with all of reality spread across it. But this is one of the greatest tricks our minds play on us. That view that seems infinite to us is actually just a tiny fragment of the universe itself. In reality, we're seeing less than perhaps 4% of what exists. Without realizing it, we're trapped inside an invisible sphere with a radius of about 46 billion light-years. Beyond its borders, more universe extends, billions more galaxies, trillions more stars, perhaps even other versions of you reading these very words. But we'll never see any of them. With no telescope humanity could build, with no technology that could exist, will we ever be able to look beyond that boundary. This isn't a prison made of walls or barriers. It's the ultimate cosmic prison with walls made of time itself. To understand how this trap works, we need to remember two fundamental properties of the universe. Light's speed is finite, and the universe's age is finite. Light takes time to travel. When we look at the sun, we see it as it was 8 minutes ago. When we look at our nearest star system, Alpha Centauri, we're looking 4 years into the past. When we look at the Andromeda Galaxy, one of the most distant objects visible to the naked eye, we're witnessing 2.5 million years ago, a time when the human species didn't yet exist. The farther we look in space, the deeper we look in time, and that's exactly where the trap closes around us. The universe is approximately 13.8 billion years old. This means the oldest light that can reach us has been traveling for at most 13.8 billion years. If any galaxy is more than 13.8 billion light-years away, its light hasn't had enough time to reach us yet. From our perspective, it's as if that galaxy doesn't yet exist. But wait, the trap is even more restrictive than that. We mustn't forget that while that light was traveling toward us, space itself was continuously expanding. That distant galaxy whose light we see today was much closer to us billions of years ago when it emitted that light. During the long time it took for the light to reach us, the universe's expansion carried that galaxy much farther away, far beyond the 13.8 billion light-year limit. Today, a galaxy whose light began its journey 13.8 billion years ago sits approximately 46 billion light-years away from us. This creates your cosmic prison cell. Everything beyond 46 billion light-years from Earth exists in what scientists call the unobservable universe. You can't see it, you can't detect it, you can't prove it exists, yet logic and mathematics tell us it must be there. Imagine yourself standing in thick fog, limiting your vision to 100 meters in every direction. There's a circle around you of what you can see. But you know the world continues beyond that fog. The observable universe is your circle, limited by that fog. The real universe potentially extends infinitely in all directions. And here's that number that's both terrifying and awe-inspiring. If the universe is truly infinite, then your observable bubble contains exactly 0% of what actually exists. 0. Because any finite number divided by infinity equals 0. Everything we see, trillions of galaxies, trillions of stars, all that apparent vastness and grandeur might be an infinitesimally tiny fraction of reality itself, in infinity. This is one of the most humbling and shocking lessons about our place in the universe. Everything we see is essentially almost nothing. What lies beyond our prison walls? Before wondering what lies beyond our cosmic prison walls, we must understand what those walls are actually made of. The outermost boundary of the observable universe isn't empty darkness. On the contrary, that boundary is drawn by the universe's own oldest light. This light, even now racing toward us at about 300,000 kilometers per second, carries a message about the moment when reality began. It's been traveling far longer than Earth has existed, far longer than our solar system formed, even longer than our galaxy, the Milky Way, took its current shape. This light began its journey when the universe was only 380,000 years old. Back then, the cosmos was a seething soup of plasma too hot for even atoms to form. Today, we call this ancient radiation the cosmic microwave background, CMB. About 1% of the static you see when tuning an old analog TV between channels comes from this primordial light. You're literally watching creation's afterglow flicker on your screen. This radiation fills every cubic centimeter of space. It comes from every direction at once. It's the oldest thing the human eye or instruments can detect. But what makes this discovery so profound is that this light represents the edge of everything we can observe, the ultimate horizon. Before that moment, 380,000 years after the Big Bang, the universe was opaque. Light couldn't pass through. In the early universe, everywhere was like trying to see inside the sun's surface. Photons couldn't travel more than a few centimeters through that roiling plasma dense with free electrons and protons. Every photon immediately collided with a charged particle and was absorbed or scattered. Then something miraculous happened. The expanding universe cooled to a critical temperature threshold. At this threshold, protons and electrons came together to form the first hydrogen atoms. Suddenly, that cosmic fog cleared. The free charged particles that constantly blocked light were now trapped inside neutral atoms. The universe became transparent. Light could finally travel freely through space without obstruction. The first photons escaping this cosmic enlightenment are the photons reaching our eyes and telescopes today as the cosmic microwave background. This moment, known as recombination, created the ultimate horizon. We can never see before it, ever. Events during those first 380,000 years will remain forever hidden from us. It's like trying to see inside a brick wall surrounding the entire early universe. The cosmic microwave background is that wall, representing the absolute limit of observation. But this horizon isn't a static wall. Every passing second, this horizon moves. Light that's been traveling for 13.8 billion years plus 1 second is now reaching us. Our observable universe grows by 1 light second every second, about 25 billion kilometers farther every day. However, the universe's expansion complicates this simple growth. While our observable horizon expands, the actual distance to the source of that ancient light also continues increasing due to cosmic expansion. A galaxy that emitted a photon 13.8 billion years ago sits 46 billion light-years away today. We see where it was, not where it is. This creates a strange situation. We're constantly seeing space regions whose light sources are continuously moving farther away. It's like watching a film of someone walking away while the screen itself keeps getting bigger. The cosmic microwave background shows us that in that youthful period, the universe was smoother than even the smoothest glass surface, except for temperature variations of a few parts in a million. These microscopic temperature variations would eventually turn into everything: galaxies, stars, and us. But when we cross beyond this oldest horizon with our imagination, when we look behind that wall, what do we find? When we pass beyond that ultimate boundary of everything visible, the cosmic microwave background, we enter a realm where scientific evidence ends and logical inference begins. What's behind that wall? The simplest and perhaps most disturbing possibility is more of what we see. Exactly more of the same. This might sound boring, but it's actually one of the most shocking possibilities in cosmology. If you could somehow teleport 47 billion light-years away, just beyond our observable limit, you'd most likely find yourself in a region looking quite similar to here. More galaxies, more stars, more planets, and perhaps more life. The universe appears to be homogeneous on the largest scales, uniform, consistent, the same everywhere. Like perfectly mixed cake batter, every spoonful contains the same ingredients in the same proportions. When we observe the cosmic microwave background, we see evidence of this homogeneity. Those tiny temperature variations we detect are distributed smoothly and consistently across the entire sky. This smoothness tells us something profound about what lies beyond our field of view. If our observable universe contains roughly 2 trillion galaxies, then a region of the same size just beyond our horizon should also contain roughly 2 trillion galaxies, and the region beyond that, another 2 trillion more. This pattern continues forever, or at least far beyond our comprehension. And here's where this idea becomes psychologically disturbing. If space is truly infinite and homogeneous, then every possible arrangement of matter within a given volume must repeat somewhere. This isn't mystical thinking, it's mathematical necessity. If you have infinite space and a finite number of ways to arrange a limited number of particles, repetition becomes inevitable. Imagine shuffling a deck of cards infinitely many times. Sooner or later, you're bound to get the same sequence twice. The universe works similarly, but with atoms instead of cards. This means other versions of you reading these words exist, not metaphorically, literally, in regions of space so far that their light can never reach us. Quantum mechanics has arranged matter in every possible way, including arrangements identical to your current configuration. There are versions of you who decided to stop reading this sentence, versions who were never born, versions where Earth's history unfolded completely differently. But this assumes the universe beyond our horizon looks the same as inside. What if it doesn't? Recent observations hint that our local region might be somewhat unusual compared to the rest of the universe. We appear to live in a cosmic void, a region with lower than average galaxy density. If true, traveling beyond our observable horizon might take us to space regions filled with more density, more galaxies, more black holes, more activity. Or conversely, it might take us to regions that are almost completely empty. Bold theoretical models suggest cosmic inflation, that rapid expansion in the first fractions of a second might have created regions with vastly different characteristics, pocket universes with different physical constants, different particle types, completely different laws of physics. These pocket universes might exist just beyond what we can observe, operating under rules that would make our physics textbooks worthless. But beneath all this speculation lies an even more fundamental question. What if the universe isn't infinite? This raises a series of disturbing questions. What's beyond its boundaries? How can space itself have an edge? What happens if you try to cross that edge? These questions lead many scientists to prefer infinite universe models despite their conceptual challenges, because in an infinite universe, there's no concept of outside, making the "what is it expanding into" question meaningless from the start. Our current measurements show our universe is either infinite or so large that any curvature is undetectable. The simplest interpretation is that space extends infinitely in all directions. And this brings us back to that mind-bending thought from the beginning. Everything we see is essentially almost nothing. The beautiful paradox of infinite expansion. The idea of an infinite universe expanding creates one of physics' most beautiful paradoxes. Our minds immediately ask, how can you make infinity bigger? Mathematics tells us this should be impossible. Adding anything to infinity still equals infinity. Multiplying infinity by 2 still equals infinity. You can't add to something that already contains everything. This seems like a logical dead end. Yet when we point our telescopes at the sky, the reality we see is unmistakable. Space is expanding everywhere. The solution to this paradox lies in redefining what expansion actually means. When the universe expands, it doesn't mean it's becoming more infinite or adding new area to its infinity. It means the scale of space itself is increasing. To grasp this better, imagine an infinite sheet of graph paper where each square is 1 centimeter wide. This paper extends infinitely in all directions. Now imagine we magically stretch this paper so each square is now 2 centimeters wide. The paper is still infinite. It still has an infinite number of squares, but the distance between any 2 points we marked has now doubled. The paper itself hasn't grown. It was already infinite, only its scale has changed. That's exactly what happens during cosmic expansion. The universe doesn't become more infinite. Space's scale factor increases, causing all distances to grow proportionally. A galaxy 100 million light-years away today was 50 million light-years away when the universe was half its current size. Distance grew with space's scale. This leads to a disturbing but logical conclusion. If the universe is infinite now, it must have been infinite at the Big Bang too. This completely transforms our mental image of the Big Bang. The Big Bang wasn't matter and energy exploding from a single point into empty space. It was an expansion and cooling event happening simultaneously at every point in infinite space, filled with infinite energy. Visualize this in your mind. The Big Bang happened everywhere, throughout all of infinite space at the same time. No center, no edge, no outside. Just infinite space that suddenly began expanding and cooling. Every point in the universe can claim to be the center of expansion because expansion looks exactly the same from every point. You're sitting at the exact center of your own personal Big Bang right now, just as a hypothetical observer in a galaxy billions of light-years away sits at the center of theirs. This infinity perspective solves some cosmic mysteries while creating new ones. It explains why the universe looks the same in every direction from our viewpoint. In infinite homogeneous space, every location is equivalent to every other. It also explains why we see no evidence of an edge or center, because there's no edge or center to see. But it raises a disturbing question. If the universe contains infinite matter and energy, how do we avoid infinite density? The answer lies in remembering that density is matter divided by volume. Even if both matter and volume are infinite, their ratio can still be finite. The universe can contain infinite amounts of matter spread across infinite space and still maintain a specific average density, about 5 hydrogen atoms per cubic meter. And here's where the paradox becomes personal. In an infinite universe, every possible event will occur infinitely many times. Not just your repetitions we discussed earlier, but every possible story in every possible version is being lived somewhere in that vast expanse. Every tragedy, every triumph, every moment of beauty, and every act of cruelty. If this disturbs you, consider the alternative. A finite universe raises equally disturbing questions. What's beyond its boundary? How can space itself have an edge? These questions lead scientists to prefer infinite models, and our current observations support that our universe is either infinite or too large to detect any curvature. This means the expansion you're observing isn't creating new area like adding rooms to a house, it's just stretching already existing infinite fabric. If space is just stretching infinite fabric, we're left with the question of what triggers this stretching itself. What drives this relentless, everywhere expansion? The answer perhaps lies in the universe's most mind-bending and counterintuitive reality. The universe is producing new space from pure nothingness at an unimaginable rate. Every second, the volume of observable space increases by trillions upon trillions of cubic meters. This number is so colossal that if you tried to reach it by counting one number per second, you'd need billions of times longer than the universe has existed. And all this new space emerges from something called the quantum vacuum. The quantum vacuum isn't that empty, quiet nothingness we picture in our minds. On the contrary, it's a seething sea of virtual particles, appearing and annihilating each other in time intervals shorter than the smallest measurable moment. This process, known as quantum fluctuation, fills every point in space with energy. Even in the most perfect vacuum, this quantum activity continues non-stop. And here's the mind-bending part. This vacuum energy has gravitational effects. But unlike matter, which creates gravity that pulls things together, vacuum energy creates repulsive gravity. It pushes space apart. And this process creates a self-feeding cycle. The more space you have, the more vacuum energy you have. The more vacuum energy you have, the more space expands. The more space expands, the more room there is for new vacuum energy. This is a runaway process known as inflation. In a tiny fraction of the first second of the universe, this process went crazy. Space expanded faster than light could travel. This doesn't mean anything moved through space faster than light. It means space itself grew faster than light could traverse it. Imagine trying to walk on a treadmill accelerating faster than you. No matter how fast you run, you'll never reach the starting point. A region smaller than a proton reached roughly basketball size in less than a trillionth of a trillionth of a trillionth of a second. This might sound like nonsense, but quantum mechanics requires it. Heisenberg's uncertainty principle says energy can be borrowed from nothing, provided it's paid back quickly enough. During inflation, the universe borrowed colossal amounts of energy to create new space, then used the expansion itself to pay back that debt. It's like taking out a loan to buy a money printing machine, then using the printed money to pay off the loan. The process worked so well, it overshot its target. Inflation was supposed to stop after creating enough space to solve certain cosmological problems. Instead, it continued, creating far more space than necessary. Our entire observable universe represents just a patch, a pinprick-sized piece of this massively inflated region. But the strangest part is this process continues today. Current expansion isn't as violent as inflation, but it operates on similar principles. Dark energy, comprising about 68% of everything, behaves exactly like vacuum energy. It fills space uniformly and creates repulsive gravity that boosts expansion. As the universe grows, more dark energy emerges to fill new space. This violates all our intuitions about energy conservation. Energy cannot be created or destroyed, yet expansion seems to continuously create new dark energy. The resolution to this paradox lies in understanding that gravitational potential energy is negative. As space expands, matter becomes more dispersed, increasing gravitational binding energy, negative energy. This negative energy balances the newly created positive dark energy. Even as the universe creates infinite new space, it maintains perfect energy balance. This process seems set to continue forever, or at least longer than the human mind can grasp. Every moment brings new space, new dark energy, and accelerating expansion. The universe grows not because it needs a room to expand into, but because expansion creates its own room. The evidence that made the impossible real. The idea that in the universe's first moments, a region smaller than a proton reached colossal size in a time span quadrillions of times shorter than an eye blink sounds so fantastic, so counterintuitive, that without solid evidence, it couldn't be more than speculation. So what's our proof that this seemingly impossible story actually happened? The answer, ironically, lies hidden in old TV's static screens. Some of that seemingly meaningless noise carried the faint echo of cosmic history's most violent event. In 1964, two radio astronomers working at Bell Labs, Arno Penzias and Robert Wilson, were trying to eliminate an annoying background noise from their antenna that they just couldn't get rid of. No matter what they did, there was constant, persistent hissing in their data. They cleaned the equipment of pigeon droppings. They recalibrated their instruments. They pointed the antenna at different parts of the sky. The noise never went away. Because that noise wasn't coming from equipment or Earth. It was the echo of creation itself. What Penzias and Wilson accidentally discovered was the cosmic microwave background, CMB, the Big Bang's afterglow stretched and cooled by 13.8 billion years of expansion. This discovery earned them the Nobel Prize and provided the most direct evidence we have for the expanding universe model. What makes this radiation so important is that it carries expansion's signature literally stamped into its own wavelength. When this light first escaped from the early universe, it was bright, visible light with a temperature of about 3,000 degrees. But as space expanded, light's wavelength stretched along with it. What began as dense, visible photons transformed first into infrared radiation, then microwave radiation, and finally radio waves. Today, this ancient light reaches us at a temperature just 2.7 degrees above absolute zero. The cosmic microwave background is nearly perfectly uniform, except for variations of a few parts in 100,000. And this uniformity is precisely what inflation theory predicts. Without inflation's rapid expansion, different regions of the universe wouldn't have had time to reach thermal equilibrium with each other, and we should see dramatic temperature variations across the sky. Instead, we see near-perfect uniformity. This shows the universe was once incredibly small and connected, then equally ironed smooth in all directions. But those tiny temperature variations that do exist tell an even more remarkable story. They represent quantum fluctuations that inflation stretched from subatomic scales to cosmic scales. An energy fluctuation once occurring in a region smaller than a proton's width transformed into a structure thousands of light years wide within fractions of a second. When inflation ended, these fluctuations were left frozen as permanent marks in the universe's fabric. These marks are still visible today as tiny temperature differences in the cosmic microwave background, the universe's first map. Some regions are slightly hotter than average and therefore slightly denser. Others are slightly cooler and less dense. This temperature map is the universe's baby picture, an image of those quantum fluctuations magnified by inflation. After these initial seeds were planted, gravity took over. Slightly denser regions had slightly more gravitational pull on surrounding matter. Over millions and hundreds of millions of years, these regions steadily attracted more matter. Dense regions became denser. Less dense regions emptied further. This was the formation of the universe's vast structure, known as the cosmic web. Dense regions became the web's bright filaments and nodes where galaxies and galaxy clusters formed. Empty regions transformed into the vast cosmic voids between them. This has profoundly deep meaning. The Milky Way galaxy you live in, the sun warming your planet, the atoms in your body, all owe their existence to a random quantum event in the universe's first moments. You descend from quantum foam. If inflation hadn't magnified those initial quantum uncertainties to these colossal scales, the universe would have remained perfectly smooth with no density differences for gravity to grasp. No structure would have formed. The universe would have remained forever uniform, boring, lifeless gas cloud. But inflation raises a disturbing possibility. If it happened once, can it happen again? The same quantum fields that drove primordial inflation might still exist, waiting for the right conditions to trigger a new period of exponential expansion. This could happen here, now, without any warning. A new inflation bubble could nucleate anywhere in space, expanding outward at light speed, destroying everything in its path. Inside this bubble, new laws of physics would apply. Our atoms would disintegrate, our natural laws would cease functioning. We'd never see it coming because it expands faster than light reaching us. This terrifying possibility pales beside inflation's most mind-bending consequence. What if our universe is just one bubble in an infinite sea of expanding realities? This idea brings us to science's edge, the dizzying realm of the multiverse hypothesis. The multiverse, when one universe isn't enough. Cosmic inflation theory doesn't just explain our universe's beginning, it also brings us to the threshold of a much larger, much more mind-boggling possibility, the multiverse. Though this idea sounds like science fiction, it's actually one of inflation theory's most natural and logical consequences. If inflation happened once, quantum mechanics suggests it must be happening continuously throughout a larger space called the multiverse. According to this scenario, our universe is just one of countless bubbles in an infinite sea of foam. In this model, known as eternal inflation, random quantum fluctuations can trigger new inflation periods anywhere, anytime. Each period creates a bubble universe that expands, cools, and potentially develops its own galaxies, stars, and planets within itself. This idea transforms the definition of universe. Our universe is everything born from our Big Bang, subject to our laws of physics. But this might not be the only reality that exists. What makes this possibility so disturbing is that each bubble universe could have completely different physical laws. The strength of gravity could differ, electron mass could change, the number of spatial dimensions might not equal 3. Most of these universes would be unimaginably alien and lifeless wastelands. In some bubbles, gravity might be so strong that stars instantly collapse into black holes. In others, gravity might be so weak that matter never clumps to form structures. Some universes might lack electromagnetic force, making chemistry impossible. Others might remain in eternal inflation before atoms can form. The vast majority of bubble universes would be sterile and lifeless. But in an infinite multiverse, even the most improbable possibilities must occur somewhere. However improbable our special combination of physical constants seems, infinite bubbles mean infinite opportunities for constants to align perfectly for life. We exist in a habitable bubble not because we're special, but because we can only exist in a habitable bubble. This reasoning, called the anthropic principle, explains why our universe appears so finely tuned for life. We don't live in a universe designed for us. We live in the rare kind of universe where observers like us could evolve to ask such questions. But the multiverse concept brings deep philosophical problems. If there are infinite universes, then every event happens somewhere. Every decision you didn't make is made by another version of you in another bubble. Every tragedy you avoided befalls another version of you elsewhere. Every dream you never reached comes true for a different you in a different reality. The multiverse contains infinite copies of everyone experiencing everything everywhere. This infinite repetition makes the concept of uniqueness meaningless. If infinite versions of you exist, you're not unique. If every possible choice is made by some version of you, your choices lose meaning. If infinitely similar universes exist alongside yours, your universe isn't special. Yet the multiverse remains unobservable. By definition, other bubble universes lie beyond our cosmic horizon. Their light can never reach us. Their mass and energy can't affect us. We can never prove their existence or determine their properties. The multiverse concept makes untestable predictions. This troubles many scientists who argue untestable theories don't count as science. However, inflation's mathematics strongly suggests eternal inflation and bubble nucleation. The same quantum field equations explaining our universe's early expansion also predict ongoing expansion and bubble formation in the larger multiverse. If we accept inflation, we might have to accept its consequences. Recent observations have begun testing inflation's predictions more precisely. The cosmic microwave background contains subtle patterns matching inflation theory remarkably well. While these observations strengthen confidence in inflation, they also indirectly support the multiverse concept. Perhaps the best evidence for infinitely many other worlds is the one we're living in, when time itself stretches. Heat death's inevitable end in the infinite distance isn't expansion's only consequence. Expansion doesn't just stretch space's fabric, it also stretches time's fabric, which is unified with it. As Einstein showed us, space and time aren't separate entities, they're parts of a single whole called space-time that bends together, ripples together, and expands together. This has profound and strange effects on how the universe ages and how we perceive it. We see this effect most clearly when observing distant galaxies. Events in a galaxy rapidly receding from us due to expansion appear to unfold in slow motion relative to our reference frame. This phenomenon is known as cosmological time dilation. For example, a supernova explosion that reaches maximum brightness and fades over 3 weeks in a nearby galaxy might take weeks or even months when observed in a galaxy billions of light years away, rapidly receding. This doesn't mean clocks in that galaxy actually run slower. For an observer in that galaxy, everything is normal. This effect results from what happens to information about those events as it reaches us. Light carrying events to us passes through continuously expanding space during its billions years journey. This expansion not only redshifts light by stretching wavelength, it also stretches temporal information carried by those light waves, the rhythm of events. Time intervals between light pulses stretch. The universe literally stretches time itself like a rubber band. This temporal stretching gives us important clues about the nature of the universe's evolution. The early universe didn't just contain more compressed space, it also contained more compressed time. This means grand cosmic processes taking billions of years by today's standards happened much faster in that dense early cosmos. The formation of first stars, first galaxies, first black holes all occurred in a universe where time flowed at a different rhythm than today. But expansion's effect on time doesn't just change flow rate, it also makes the concept of simultaneity meaningless on cosmic scales. In our everyday experience, two events happening simultaneously means they happen at the same time for everyone. But relativity and cosmic expansion shatter this intuitive assumption. Events appearing simultaneous to you occur at completely different times for an observer in a distant galaxy. There's no universal now moment that applies everywhere in the universe that everyone can agree on. This means when we ask, "What is the universe doing right now?" we're actually asking a meaningless question. The concept of now is only local, valid at your space-time point. Now for a galaxy billions of light years away is completely different from your now. As expansion accelerates, these temporal effects become more dramatic. As dark energy's power increases, space stretches faster, which also accelerates time stretching. Future civilizations in our galaxy will observe much more extreme time dilation effects when looking at distant galaxies than we see today. Eventually, expansion will stretch time so much that events in distant galaxies will appear completely frozen from our perspective. Though light from those galaxies continues reaching us, the story it carries will seem stuck in a single frame of infinite slow motion. This is among the deepest proofs of how strange and elastic the universe's fabric can be, far beyond our everyday experience. Time isn't the fixed universal metronome we think it is. It's a dynamic phenomenon that stretches, bends, and flows personally with the universe's expansion. The universe erasing its own history. The universe's accelerating expansion doesn't just lead everything toward a cold ending in the distant future, it also creates an even more insidious effect. The universe is slowly erasing evidence of its own past. Billions of years from now, future civilizations arising in the Milky Way will look at a vastly different universe from what we see today. A deceptively simple universe where they'll reach completely wrong conclusions about cosmic history. This happens because dark energy moves distant galaxies away from us ever faster. In about 150 billion years, all galaxies outside our local galaxy group will have crossed the cosmic horizon. This means their light will lose to space's expansion speed and never reach us again. From future observers' perspective, these billions of galaxies will simply have faded from view. What will scientists living in that distant age see when they look at the sky? They'll observe a universe appearing to contain only a few dozen galaxies surrounded by completely empty space. By then, the Milky Way, Andromeda, and our other local neighbors will have merged through gravity's effect, forming a giant elliptical galaxy. This isolated island universe will appear to them as the entire cosmos. Our clearest evidence for the Big Bang, the cosmic microwave background, will also have vanished by then. Expansion will have stretched this ancient radiation to wavelengths longer than the observable universe itself. Future instruments won't detect any trace of this primordial light. Without the microwave background, future cosmologists will lack the strongest evidence that the universe once had a hot, dense beginning. The redshift-distance relationship that first showed us expansion will also become unmeasurable. Without distant galaxies to observe, future astronomers will never discover Hubble's law. They'll have no way to detect space stretching. Their universe will appear completely static, unchanging. These future scientists might develop completely different cosmological theories. They might conclude their single giant galaxy has existed since eternity in infinite, unchanging void. They might never imagine their cosmos was once filled with billions of galaxies receding from each other due to expansion. They'll live in a universe stripped of its own history, its own origins. But this loss of cosmic perspective extends even deeper. Future observers will also lose access to information about physical laws governing the early universe's evolution. Nuclear processes forging first elements ended billions of years ago, Evidence of Big Bang nucleosynthesis will remain only as barely readable traces in old stars' chemical composition. These future civilizations will face a deep epistemological crisis. They might possess the same intelligence and technological capabilities as modern humans, but they'll observe a universe yielding few clues about its nature. Their scientific method will function perfectly, but it will lead them to false conclusions about reality. This inevitably raises disturbing questions about our own cosmic knowledge. Could we be similarly deceived by observing the universe at a particular age? Might we be missing critical evidence that was visible to earlier observers but has long since faded beyond detection by our time? Perhaps civilizations arising shortly after the Big Bang could observe phenomena forever hidden from us. This is one of expansion's most ironic consequences. While expansion creates the dynamic foundation allowing complex structures like galaxies, planets, and life to emerge, making the universe interesting, that same expansion systematically erases evidence of its own history, making the universe incomprehensible to its future inhabitants. Expansion sets the existence stage while slowly burning all notes about how that stage was set. This means the universe offers us only a limited time window to understand its own story, and by chance, we're living when that window is still open. Coming full circle. At the end of our journey, we return to that first question echoing in our mind's depths. What is the universe expanding into? We've seen this question as like asking, what's north of the North Pole? A logically flawed question where concepts exceed their own boundaries. But beyond this logical answer lies a deeper, more intuitive truth. When we understand this truth, the question itself transforms, reshaping our relationship with the universe. When we ask, what is the universe expanding into, we make an assumption that seems perfectly reasonable but is actually impossible. We assume expansion needs a pre-existing space to expand into, like a balloon needs air or a city needs countryside. But the universe isn't like a balloon. The universe is space itself. When space expands, it doesn't grow into something else. As it grows, it creates the very concept of something else. There is no outside because the universe defines what outside means. This isn't a limitation of human language or a failure of scientific imagination. It's a fundamental feature of reality. Before expansion, concepts like into and outside don't exist. Expansion doesn't just create more space, it creates the logical framework making spatial relationships meaningful. The universe isn't expanding toward anything, because as it expands, it creates the concept of anything itself. Think of it this way. It's like asking what caused the first cause, or what contains the container of everything. These questions assume categories that only become meaningful after what you're asking about already happened. The universe grows not by becoming more universe into non-universe, but by becoming more universe. This realization transforms our understanding of cosmic expansion from a mechanical process into something much deeper. Expansion isn't just the universe growing, it's reality itself creating itself from nothing. Every cubic centimeter of space coming into being creates new possibilities for matter, energy, structure, and complexity. The universe isn't expanding toward a predetermined destination, it's expanding toward infinite potential of what could be. We're not passengers in a cosmic vehicle heading toward a goal. We're part of reality's process of creating itself. Our consciousness, our questions, that desperate need to understand what the universe is expanding into, all are expressions of the universe beginning to know itself. The expansion we observe isn't separate from us. We are the expansion, space, time, matter, and energy organizing itself into patterns complex enough to ask questions about their own existence. When we realize the question, what is the universe expanding into, is fundamentally flawed, the cosmic expansion paradox resolves, while being replaced by an even deeper mystery. If the universe creates its own space and time, if it serves as both its own stage and audience, then what we call existence might be far stranger than any science fiction imagined. Perhaps we live inside a self-existing, self-sustaining process with no beginning or end, no inside or outside, no purpose beyond the magnificent fact of its own becoming. The universe expands into itself, creating infinite space for infinite possibilities, including the possibility of beings like us, gazing in wonder at this entire impossible, beautiful process. The question, what is the universe expanding into, took us on a journey through inflation and dark energy, multiverses and quantum foam, to time's beginning and end. But perhaps the deepest answer was always before our eyes. The universe expands into mystery, into curiosity, into more questions, more discovery, those moments when we realize we're part of something far greater than ourselves, yet intimately connected to even our smallest thoughts. We are the universe asking, what am I expanding into? We are expansion asking, where am I going? We are space and time awakening to their own existence, marveling at the infinite creativity of the process that made us. And in this moment of realization, the question stops being a puzzle to solve. It becomes a celebration of existence's own magnificent impossibility. Expansion isn't movement toward a destination, it's the rhythm of existence itself. Every moment, the universe isn't just growing, it's becoming more itself. And we are both witness to and part of this becoming. This isn't a journey taking us somewhere, it's the journey itself. And in this journey, we don't need to search for a destination outside, because all the scenery, all the meaning lies hidden in the journey itself, in the expanding universe itself. This thought isn't an ending, but a new beginning, a moment of profound understanding, transforming our relationship with the universe from being a passenger to being the journey itself. And so, at our journey's end, we've come full circle, realizing the question, what is the universe expanding into, contains its own answer. It's not going anywhere. It's just becoming more itself every moment toward the infinity of its own potential. And perhaps that's the most peaceful thought of all, showing the universe isn't in a hurry to reach a destination, but exists in that quiet, continuous rhythm of simply being. Now let this thought spread through your mind like a wave. Just as the universe needs no outside to expand into, your mind needs no place beyond thoughts to rest. Peace is already here. Silence is already within you. Take a deep breath and feel your lungs' quiet expansion. And now as you slowly exhale, imagine all the questions, all the curiosities, all the complexities the day brought drifting away with that breath toward the universe's infinite expanse. You no longer need to search for answers. You no longer need to try understanding. Notice your body's weight in bed, gravity's gentle, reassuring touch. This too is part of the universe, a bond holding you here in this moment. With this bond's security, let your muscles relax. Let your mind slow down. It's not just the universe expanding tonight. Your consciousness can expand from thought's narrow boundaries toward dream's infinite, boundless realm. You don't need to struggle to get there. Like the universe's expansion, This too is a natural, effortless process. Just allow it. Feel yourself as part of this quiet, continuously becoming universe. You're also a thread in that expanding fabric, and now it's that thread's time to rest. Let your mind quiet like that peaceful emptiness between stars. Let your body find peace like a galaxy's slow, graceful rotation around its own center. Our journey tonight ends not with an answer, but with a feeling. The feeling that everything is as it should be, and you're at the very heart of this great, quiet flow. Sweet dreams.